most interesting part of my job is the broad range of science and technologies that I get to review on a daily basis. But I also enjoy when the technologies that I've worked with get transferred out to the marketplace to make people's lives better. That's also very rewarding.
So the issue of clean energy, the issue of the environment, the issue of taking where we are today and moving ahead in all different directions really excites me. There's nothing that is easy in energy. If you're trying to site a windmill, if you're trying to put a solar panel in place, you're always going to have pushback. So there's so much conversation, and in that conversation, change and good opportunities arise. So I get totally excited on a daily basis by what I do.
There are a number of things that I find very exciting about my current role. And one is that I come to a place each and every day that impacts the way that energy is developed and harnessed nationwide. The other thing that excites me about this job is the opportunity to work internationally with our colleagues around the world, but also women in energy, and to work on issues of common interest and tackle common challenges.
Well, I think technology has an amazing role to play in helping us bridge and leapfrog some of the solutions of the past and help to really provide a more equitable future to many hundreds of thousands, in fact millions of people around the world. And so for the work I do, it's really exciting to see how the work domestically here in the US, particularly with a lot of the advances on clean energy solutions, can then also be taken overseas and applied to help make other people's lives better. So that just really excites me.
So I think that what I've been able to be a part of with Cummins in reducing emissions of engines over the past decade, as well as improving efficiency at the same time, really has an impact on the world and on the users of energy in the form of a diesel or natural gas engine. I really enjoy putting together diverse teams of experts, people that are really good at something, that can then get together and work on a difficult problem where their individual skills and differences actually complement each other and improve the answer that that team can come up with. So I enjoy finding people's motivation and helping them do more of that as part of a diverse, capable team working on a difficult problem.
Hi, good afternoon. Welcome to the 4th annual C3E Symposium. I'm Martha Broad. I'm the Executive Director of the MIT Energy Initiative, or MITEI, as you will hear us call ourselves. I see a lot of old faces and new faces, and I'm really pleased to see you all here. We're going to have a great day and a half together. I want to take a moment to thank our sponsors, whose logos you see here. We have many sponsors, and I'd like to just go through the list with you. It may sound cliche, but we absolutely would not be here without them. So they are Cummins, Lockheed Martin, Sabancı Group, all the way from Turkey. They're Energisa and Industry Group companies. Shell, Solar City, Southern California Edison, GE, Walmart, the Massachusetts Clean Energy Center, the Alliance for Sustainable Energy, the Brattle Group, Hawaiian Electric Industries, NextEra, and Hogan Lovells. So thank you to our sponsors very much. And I also want to thank our team, which is a DOE and MIT Energy Initiative team that has been working very hard for many months. Caroline McGregor, Desiree Pipkins, who can't be with us, the team from Energetics that works closely with DOE, my own team, many of them are here, and I might point out that there is gender diversity in that group. We have some wonderful men who are joining us from MITEI, and some of them are students that we employ. So our team is Carter Smith, Ashley Cryan, and Debbie Kedian. So thank you to everybody for working so hard. And Finally, I would like to introduce you to somebody who's very special to me and a big supporter of the C3E initiative, and that's my boss, Bob Armstrong. Bob has mentored many women, students and faculty, and men over his 40-plus years here at MIT. And he started the MIT Energy Initiative along with Secretary of Energy Ernie Moniz and then MIT President Susan Hockfield, and was previously the chair of the Chemical Engineering Department here at MIT. Bob, in that capacity, mentored the current chair of that department, of the Chemical Engineering Department, Professor Paula Hammond, who will be joining us in a few moments. So Bob, please join me. Bob Armstrong.
Thank you very much, Martha. It's a pleasure to be here, and I'd like to add my welcome to you, along with that of Martha's. As she mentioned, this is the fourth edition of the C3E Symposium and Award Ceremony, and it's been a real pleasure doing this together with DOE over these past 4 years. As you may know, or as Martha mentioned, the goal of this C3E Symposium program is to work to engage more women throughout the energy sector and at all levels. And we need that more today than ever as we face some pretty daunting challenges of providing more energy to more people around the world, and at the same time decarbonizing the energy system. So this is clearly an all-hands-on-deck challenge to us globally. I'd like to also mention something about what we're doing right now at MIT and at the Energy Initiative in particular. We are 2 weeks ago, actually 2 weeks ago and 2 hours, MIT released its Climate Action Plan, which is a synthesis of conversations across campus over a year. And the Climate Action Plan has quite a few different pieces to it. I'd like to highlight one piece of that, which is in MITEI's court, which is to develop a set of 8 low-carbon energy centers to help us focus our talent and to engage broadly with energy, with the energy industry in a broader range of the energy business space than we have done yet to date. These 8 centers are quite diverse. We run from solar energy, storage, advanced materials, nuclear energy, carbon capture, use and sequestration. In nuclear, I should have said both fission and fusion are on the table. Some very interesting stories there. The grid and energy bioscience. So it's a really interesting set of core focused activities in low carbon energy. And the faculty on the campus are quite excited about coming together, working together across campus and working with industry partners to develop low-cost technologies in these areas for the future. And we're delighted to have you here as key partners for us in moving that agenda forward. So I'd like now to introduce Paula Hammond. As Martha mentioned, Paula is the current head of the Department of Chemical Engineering here at MIT. She's been on the job since July. So she's already ramped up and deeply engaged and doing a great job. I've known Paula since she came to campus. I was involved in recruiting her while our then department head was on sabbatical. I don't know if you remember dinners out convincing you that this was the right thing to do. She has a long history at MIT. She got her undergraduate degree here in chemical engineering in the 80s. In chemical engineering at MIT, we kick our undergraduates out after they get their SB degree and make them go do graduate school somewhere else. Paula went to Atlanta to work in industry, actually, at Motorola for a couple of years, before she went to Georgia Tech, where she got her master's degree, and then came back to MIT for a PhD. That time we actually didn't let her go, so we knew a good thing when we had it. So we've had Paula since her PhD at MIT, minus a short stint as a postdoc. Paula's known worldwide for her work in material synthesis. She is an expert at the design of tailored functional materials for a variety of applications. She's known for very clever chemical synthesis, for understanding the principles of secondary interactions in polymers, which are important in self-assembling systems. She's developed novel processes to allow you to scale up production of these materials, and she's really good at choosing application targets for these materials. Two application areas in particular, which you'll recognize as important, are cancer treatment. She's very much involved in the Cancer Institute here at MIT, and energy. She has worked on developing new materials for a variety of energy applications, including ultracapacitors, batteries, solar cells, and so on. So she's really a versatile researcher, and one that's got a lot of depth in what she does. So with that, it's a pleasure to welcome Paula to the podium.
Thank you. It is really great to be introduced by Bob. He is definitely one of the first faces to bring me in and mentor and coach me when I started as a faculty member, so there's some real meaning to that. I'm really excited to be speaking to you today because what I'm going to talk about reflects a little bit of the research that we've been doing in my lab, but also reflects how important it is to have a diverse set of voices involved in addressing these very real scientific and engineering problems in energy and sustainability. I think in particular, our voices as women are important. I think, I love the fact that at MIT, I feel like I've always been a beneficiary of a hugely diverse set of people. Hearing voices from different countries, from different genders and races and different perspectives has really enriched my science. And I think in particular in this part of our role as scientists, engineers, and technologists to take care of the world and make sure that it is sustained over a long time period, that as women we bring a very important and unique perspective. I've also had a really wonderful opportunity to work with some rock star women scientists and engineers, and I'll point that out as I talk. So in our lab, we actually use a very simple assembly technique. I'm a polymer scientist, and we work with charged polymers. So we work with a very simple technique in which we alternate the adsorption of positively and negatively charged polymers. It's a very simple method. It involves immersing a substrate in water solutions which contain these multivalent charged materials. First, a positively charged material will adsorb, you rinse, and then a negatively charged material will adsorb. It's based on self-assembly principles, so the thickness of these layers that we're building are really only molecules thick. They're only a few nanometers per adsorption cycle. We can also adsorb other materials, and I'll get to that in a minute because it allows us to incorporate active nanomaterials into these thin films. Now, we process this, I'm showing these beakers, but in reality, we also use a rapid assembly method called spray layer by layer assembly. Rather than dipping a substrate back and forth, we can actually apply a jet and spray these materials back and forth. And that spraying actually allows us, here we're showing the back and forth, allows us to coat very complex substrates, both smooth and continuous ones that are relevant for certain kinds of applications, such as the generation of a thin film electrolyte for a battery, and porous and very complex ones in which we can actually coat something that gives us a huge amount of surface area that might be used for an electrode. And this lab scale process has actually been adapted to a very large scale by a member of my lab, Kevin Krogman, who started a company called SPIA, which developed an industrial scale version of this process. This process was then ultimately sold to 3M. So hopefully we get to see various forms of this technique and technology in the world. And this is just showing how large these films can be. Can be quite large, which is appropriate if we want to adapt this to a range of applications from the micro to the macro scale. And in particular, we've looked at a range of different hybrid composite materials we can make with these films that range from thin film batteries that are flexible, as you can imagine, would be very interesting for us, but also fuel cells, the proton exchange membranes in fuel cells, and sensors and micro batteries. And for that reason, we use this fairly universal tool to generate materials that can combine different material systems together in a very intimate fashion. It allows us to take something that is a pure insulating material for electrons, but allows the flow of ions, and connect that to something which enables rapid flow of electrons. We can actually get some very interesting systems. Our first work actually was in designing a membrane, a solid material that would actually limit the rate of penetration of methanol, but would promote the transport of protons for methanol fuel cells. And in that work, we were able to develop some fairly exciting materials that gave us the basis for a very thin film proton exchange membrane that could be used for a range of different fuel types. And this gives you just some of the things we were thinking about and looking at that time, how we could enhance the mechanical properties of these systems. And we found that by using the spray layer by layer approach on a porous membrane, we could actually build a composite proton exchange membrane that had properties that exceeded some of the properties we observe in Nafion. While we were doing this work, I began to interact with another professor who's Jan Schauhorn. She, at that time, had just arrived a couple of years ago in mechanical engineering, and she started to talk to me about some of the work we were doing, that we had this interest in fuel cells. Now, she is a real electrochemical engineer. She actually, her lab is even called the Electrochemical Energy Laboratory, EEL, here at MIT. And we were a great combination, in fact, and we're working together even now on battery applications. That interaction with Jan, as you can see here, led to some very interesting things. We had a graduate student joint between us, and we asked the question, why can't we just layer carbon nanotubes with carbon nanotubes and make a very high density electrode for a battery? And the idea is we can make these batteries very thin, we can process them with water very easily, and we can actually generate a system that may give us higher power and higher storage while essentially using some fairly simple materials. So we took multi-wall carbon nanotubes, not the very refined single-wall guys, but the bulk ones that you can make with huge mass. And we treated them so that they had acid or amine groups and layered them. And we found that even with very thin films, we were able to get, if you see over on the right-hand side at that furthest curve, the black one, that we were able to get really high power and energy from the same cathode. And this was something that was very exciting. We had exceeded sort of the record at that time, but we also were demonstrating the fact that you could bring together the properties of something that acts like a battery with the properties of something that can act like a capacitor. And this led to us having a bit of a crew between our two labs. And this gives you an idea of that. This is me and Jan standing for the publication of one of these papers in that area. And next to us is our joint student, Samu Lee, who's a professor now at Georgia Tech. And Jan's student, Betar Galant, who is now a professor here. So, you know, the torch passes on in ways that you can't even imagine. But I think this is one of the exciting stories about getting involved and getting students involved, getting collaborators involved, is that this spirit and joy for working on these really complex but compelling problems that lead to meaningful solutions is contagious and propels other young people forward in their careers. Now Jan and I are working on some new applications. This is actually showing some of the work in which we're trying to build capacitors using assembly on high surface area systems. But we've also been looking at creating solid versions of lithium air batteries. This is a challenging area. It would be great because we could actually use air as the opposite electrode. We have a lot of that, it's abundant, but it's challenging. And one of the challenges is that there are very few electrolytes that can withstand the oxidation processes that take place in the sort of operation of these systems. So we're looking at whether we can design new thin film polymeric low-cost materials that can take it. And this is what some of our current work is about. So I mentioned one of my great collaborations with Jan, and we continue to work together, and we continue to mentor a diverse group of students together. In the meantime, when I first met Angie, she was fairly new on campus. Angela Belcher is a professor of material science and biological engineering. She arrived at the time that we were starting efforts to really work on nano systems in our layer-by-layer approach. And we just, Angie and I just clicked. We, at first, didn't even know what we were going to work on together. We just knew we were going to work on something together. So we began to look at what happens when you try to take the systems that Angie works with and combine them with the systems that I work with. So to give you a little capsule of what Angie's work is focused on, she actually takes these non-infectious viruses. These are bacteriophage, so they attack bacteria, but not us. They tend to have long filamentous structures, extremely long. Maybe they're about just a few nanometers in diameter. Think about 4 to 8 nanometers in diameter, but they're a full micron in length, so they look like long spaghetti noodles. And essentially, she can engineer these viruses in large quantity to present different proteins on their surface. And those proteins bind different molecules, and those molecules can be converted to different natural metals or metal oxides. And it turns out that a number of those metals and metal oxides are interesting for energy applications. So Angie had been working on how to generate these nanowires and implement them. We were working on assembly of materials that could act as electrodes or electrolytes. And we began to find that when we assembled Angie's virus with our thin film, that they sort of lined up together. So you end up with a bit of an ordered mass, densely packed, of these filamentous viruses. And you can then template your material on top and create these really ordered arrays of nanowires. So we worked together. We found that the layer-by-layer system could be used as a battery electrolyte, very thin, and that the virus could be used as a nanowire electrode, very high capacity because of the surface area. And we then teamed with another friend down the Infinite Corridor, Yet-Min Chang, who is an expert on batteries, and we developed a virus battery. We've since adapted that work to look at a range of different applications. But we actually adapted it to look at solar. During that time, we had the ultimate sort of experience of meeting the president when he came to speak here on energy in 2009. And so this is a picture of the sort of science show we gave Barack Obama. And literally, we had a poster, and we stood next to it. And we, just like in high school, and we explained how our project works. You had some great questions. So here in the top, we're just describing the spray layer by layer of the solutions and the materials. And then at the bottom is the entire group that met with him that day. Angie and I are standing to my immediate left are Becky Ledusky, an NSF fellow who was working on the project and is now heading projects at Dow Chemical. And next to her is John Burpo, who is both at that time was a graduate student and a second lieutenant in the Army. So he dressed appropriately at that time. And then fellow faculty members Mark Baldo and Alex, having one of my little minutes here. Thank you, Slocum. He's unforgettable, I'm sorry about that. And so we talked about a range of different energy applications, from windmills to solar to controlled optical effects and solar reflectors. And now Angie and I are working on how we can construct or build virus-based films for solar. And this work was also done by a very promising female graduate student, Noemi, who is now doing her postdoc at Harvard and is a promising, probably potential faculty member. I think this, again, is very elegant work in which we're templating titania to create a very highly ordered but very thin device. And the idea is to lower the weight and to increase the ability to generate power, increase the efficiency in very low-cost systems. So here we were looking at ways in which we could do that and make solar something that you just sort of roll out in a film and place anywhere that you want. And this is just a picture of that. Okay, so this is my lab now. We work on a very broad range of problems, from, as Bob described, from cancer to energy. And I think one of the things that is really fulfilling about working with a very diverse group, as you can see, is getting that input from different perspectives. I'm really excited to hear about C3E, because you guys represent leaders who are actually going to engage the world in not only the science and the technology, but the message about how we have to move forward in energy and the technologies that support sustainability. I'm excited about the fact that we have the opportunity to increase the number of female voices in this crowd, because our voices are badly needed. We contribute to a very large and important group, half the world, in terms of representation, but we also, I think, have a unique perspective in what kinds of problems we address. And what kinds of problems get addressed are definitely influenced by the operators, the PIs. And so I think having more of us present will give us a really strong and balanced technological approach to addressing these really important problems. So I'd like to stop there, and I think at this point we'll pass it on. Yes. Thank you.
I think we have time for a question or two before we move on in the program. Are there questions you'd like to ask? Or?
Yes.
Do we have a rotating mic? Yeah, okay.
Hi. Hi, my name is Rose Mutiso. I'm from the U.S. Department of Energy, and I'm actually a polymer physicist by training, so this is so exciting. In DC, excellent. The energy events don't usually feature polymer physics deep dives. So. Excellent. So a lot of us here work on energy a little bit more downstream. So I remember when I was in the lab, I was doing very fundamental, actually similar work. I'm just wondering about what you guys do to translate your work and make it more useful to those of us in the energy world, especially trying to advance clean energy. Often there seems to be a huge gap between kind of what's in the lab that's exciting but ends up languishing there and not really making it downstream, and how do you kind of...
So I think those are great questions. I think there are several different answers to that. One of them is that as academicians, we create this knowledge base, but we hope that we can translate it by partnering with industry either directly or indirectly. Now, MITEI actually gives us great opportunities to partner more directly. And Angie and I have worked with MITEI to directly engage and hear what industry's needs are. And we've also had projects with companies like Samsung and ENI, and so these companies give you a voice but also an interest, and they will ultimately look at these developing technologies and invest in them. But there's a second way, at least a second way, and that second way is that it's not unusual for the actors, the scientists themselves, to launch companies that allow the translation of these technologies. And we see that happening quite a bit. Obviously here is MIT is very well known for creating an environment where this is very often an endpoint for a new technology that has a lot of promise. I think if we can extend that principle more broadly and provide resources for people who are innovating on this level, then that allows us to yield more fruit, because often the industrial support is really important. I should emphasize that, because these are the people who can actually translate these technologies. But the startups are also, they play a very unique role in creating a kind of microenvironment in which new ideas bubble up and get a chance to be tested early. So I think those are the two most important mechanisms, but I also think that the national labs play a role, because we can actually, in talking and engaging, find ways to test our technologies, to understand how to better scale our technologies, and in many cases there are handoffs of technologies in collaborations with national labs.
Just to put a number on the startups,
Yeah.
I think since MITEI started, there have been 40+ startups in energy coming out of MIT. So very, very vibrant ecosystem here. Is that a question over here?
Was that question very similar to what was asked? So I'm just going to ask the end piece of mine. Just timing. How long does it take, for instance, for virus-based thin film solar to come from your lab into reality? Is this technology like in my lifetime, or is it in a couple of years?
Now, that's a good question too, and it really depends on the technology and what kinds of driving forces are behind it. But I would say if there is, and I described several different kinds of technologies, if there's a scalable technology that is already showing some measure of meaningful improvement, and there is an industrial sponsor willing to sort of run with you, or a company. For energy, unlike sort of the bio side of things that I work on, you can actually get things started fairly rapidly. I think, and Bob will probably give a better number, so I'm going to defer to him, but in a couple of years, you can, with the right funding, you can actually get something out into test grounds that will allow you to move it. I'm going to let Bob answer a little bit of that too, because he's observed.
I think that's good, but I actually also have the impression that a lot of your work looks at how do you make these things too?
Yes.
Right, which accelerates the process.
Exactly. The ability to manufacture and to scale whatever it is you're making can make a huge difference. So with the carbon nanotube example that I gave with Jan Schauhorn, we did actually look at ways of scaling that, and so, which is why I sort of mentioned the SWIA company, and we found that once we were able to sort of scale it, we were able to have more conversations with more companies that want to sort of adapt that technology, is show that you can make it fast enough and big enough and a broad enough scale. That tends to attract investors, because they need to know the manufacturability and the consistency of the product is there.
So I think that's one thing that excites me about the work that Paula does, is that she not only looks at novel material compositions and synthesis, but how you make them cheaply. And in energy, that's really important, as you know, is how do you scale this up to do mass production on materials. So it's just exceptional work.
Thank you.
So thank you very much, Paula.
Thank you.
That's a great introduction.
Thanks.
Thanks again. That's just wonderful. Perfect.